In this video, we want to compare the Bohr model of the atom to a more advanced model which involves orbitals. To get started, I'll draw a Bohr model of a neon atom just to remind us of what that was all about. In the Bohr model, you put the positive charges in the nucleus. There may be some neutrons in the nucleus as well. Now, according to the periodic table, neon is the 10th element, so we definitely want 10 protons in our nucleus. Since neon's mass from the periodic table is approximately 20, we can assume that the most common form of neon has 10 neutrons in its nucleus as well. So I'll just draw those neutrons as red particles here. Alright, there's a neon nucleus. In the past I had said that 2 electrons could go inside a first shell here. And the black dots represent the electrons. And after that, I had said that we would have to make another energy level shell, where this one's called n equals 2. The first one was n equals 1. And in this case, there would have to be 1, 2, 3, 4, 5, 6, 7, 8 electrons in that outer shell. And this would be the complete Bohr model of the neon atom, assuming that it's a neutral atom. But what we're going to do next is we're going to look at a model involving subshells and orbitals. Now, these orbitals that are shown are actually probability distributions of where we're likely to find electrons around a nucleus in three-dimensional space. They can take a variety of shapes depending on the type of subshell. The first subshell is the most simple. That's the S subshell. And S here could be thought of as standing for spherical, because the S orbital has a spherical shape, which means that you're equally likely to find the electron in all different directions around the nucleus. But the boundary of that picture here represents the boundary of where we are 90% likely to find an electron around the nucleus. There are other types of orbitals, though, besides the spherical. We can have these, which are sometimes called lobes, and there are 6 different directions that lobes in this P subshell can point. Now, the periodic table is organized according to the different energy levels and subshells that we might find. This question asks us to list all the subshells and orbitals that would apply to a neon atom. In other words, according to the periodic table, in what type of subshells and orbitals are neon's electrons expected to be found? So if we go to the periodic table, for the first electron of a hydrogen atom, for example, that electron would be found in what's called a 1s shell. It is energy level 1, so it's row 1, and S stands for spherical shell. If you recall, in the Bohr model of the atom for hydrogen, we said that hydrogen, if it's neutral, would just have a single electron in the n equals 1 shell. So that electron is going to be found in the 1s orbital. That is a spherical orbital with an energy level of 1. If you go on here to helium, we could have a Bohr model that looks like this. It's got 2 electrons in the n equals 1 shell, according to the Bohr model. And so in this orbital model, what that's going to correspond to is it's going to have what's called 1s2. And so what that means is we're in energy level 1. It's a spherical shell, but there are 2 electrons. And so we put that superscript to represent the number of electrons that are in the orbital. So if we're going all the way to neon, here's what we'll find. We will find electrons in the 1s orbital. So the electrons that go in the second energy level for lithium and beryllium, they would be in what's called the 2s orbital. To draw these as an example, we could have a beryllium nucleus with 2 electrons in the 1s shell. And then if we go on to the next energy level, we could have 2 electrons in the second energy level. And so basically this first ring would correspond to 1s, and the second ring would correspond to what would be called 2s. When we go across the gap here to these elements, the electrons that they will fill, they will be part of what's called the 2p subshell. And that's everything that would be included in neon. So for a neutral neon atom, electrons are expected to be found, they'll be expected to be found in 1s, 2s, and 2p. In an energy level diagram, electrons are represented by arrows pointing up or down. We're going to make an energy level diagram for several atoms. Electrons will be represented by arrows pointing up or down, representing the spin of the different electrons. If an orbital holds 2 electrons, it must be true that they have opposite spin, so one up, one down. We'll also follow the rule that if a subshell holds more than one unpaired electron, then they must have the same spin. Our orbitals will be filled in the following order. You start with the 1s, then go to the 2s, and then the 2p. This corresponds to the periodic table where we fill the 1s here first, then we'll fill the 2s, and then we'll fill the 2p. After 2p, though, comes 3s. And after 3s is 3p. Let's see if we can find that in the periodic table. So sodium and magnesium, if they're neutral, would have electrons in what's called the 3s subshell. Then, to fill more electrons, we would jump across the gap here, and aluminum through argon, if they're neutral, will have electrons in what's called the 3p subshell. So far, so good. But what's sometimes a little tricky is the 3d subshell does not actually come next when it comes to where electrons will go. Where they'll go next is into the 4s subshell. And this should make sense according to the periodic table because we just got to argon. We are now going to go over here to potassium. And potassium and calcium, if they're neutral, would have electrons in what's called the 4s subshell. So those actually get filled first before 3d. Okay, so what comes next? After 4s, we will actually go up here to 3d. So if we need to fill more electrons, we're going to go here. Now a d subshell has a different shape. So the d orbitals look like this. Somewhat similar to the p, but a little more complicated. But since we are going to 3d next, we want to see that in the periodic table. And one thing that's just a little unusual about the periodic table is that the 3d subshell is not in the third row. It is here. So when we fill electrons in neutral scandium through zinc atoms, we're going to be filling what's called the 3d subshell. So where do we go after that, after 3d? Well, according to this diagram, we will now start to fill the 4p subshell, and that is going to correspond to these elements here, gallium through krypton. That is 4p. Okay, so that is our goal, is to fill these electrons one step at a time, and we'll do so in what's called an energy level diagram. So let's take a look at how the energy level diagram works. Here's an example of it. The height of each of these blanks represents the energy level that they're at. We can see that the 2p subshell has just a little bit more energy than the 2s subshell because the height from the bottom represents how much energy is in that subshell. So that is the off-bow principle. For atoms in the ground state, electrons will fill energy level diagrams from the lowest available level upward. So we're going to actually start at the bottom with hydrogen. So let's complete an energy level diagram for hydrogen. Now in the Bohr model, we know that hydrogen has just one electron. One electron in the first n equals 1 shell. So this electron is going to correspond to what is called 1s1 as an electron configuration, it's called. And we want to both write that, the electron configuration is 1s1 for hydrogen. And we also want to show it visually with a simple arrow. Now the arrow represents the electron in the 1s orbital. And that's actually all we have to do for hydrogen. When we go on to helium, we know that helium has 2 protons and 2 electrons. Maybe some neutrons as well. Both of these electrons are going to be found in the 1s orbital. However, there are 2 of them. So when we write the electron configuration for helium, we want to write 1s2. And the 2 tells us that there are 2 electrons in the 1s shell. To show that visually, we'll do an up arrow and a down arrow. And that's all we have to do for helium. We can see that the 1s orbital is complete. It can only hold 2 electrons, and it has 2 electrons. Next we'll go on to lithium. Lithium has 3 protons in its nucleus, so I'll just draw that for now. In the Bohr model, it would have a complete first shell, and we said before in a previous video that there would be 1 electron in the n equals 2 orbital. So when it comes to the energy level diagram here, we're going to want 1 upward pointing arrow for 1 of the electrons in the inner shell. There'll be another electron in that first shell. That's n equals 1, of course. And since we have just 1 electron in the second shell, we can draw this. And so this is going to correspond to, as an electron configuration, 1s2, 2s1. We're still in a spherical type of shell. We haven't gone to the p type of orbital yet. And we can see that clearly here in the periodic table. We're at lithium, where we filled the 1s shell. We went down here to now we're in the 2s shell, and that's why our electron configuration is going to be 1s2, 2s1. Alright, let's add 1 more electron to make beryllium. We'll have an up and a down for the inner shell. And now we're going to have an up and a down in that second 2s shell as well. So this is going to be represented as 1s2, 2s2. That is beryllium's electron configuration. For boron, we're going to have everything that beryllium had and more. So the 1s will be filled, the 2s will be filled, and we can see we are now going to jump across to the 2p type of subshell. And so to represent that, we just need 1 electron in the 2p orbital there. Our electron configuration will be 1s2, 2s2, 2p1. We're going to continue with this same pattern, and for carbon, there is one interesting thing that happens here, and it comes from what is called Hund's rule. Hund's rule says when there's more than 1 orbital at the same energy, such as in the p subshells, electrons will distribute across the orbitals to remain unpaired with their spins aligned until there are enough electrons in the subshell that it becomes necessary for them to pair up. So what this tells us is that the next electron will not go here. Instead, it'll fill the next p orbital, and we won't have paired electrons with opposite spin until it's absolutely necessary for them to do that. So this is going to be, as an electron configuration, 1s2, 2s2, 2p2. Another way of writing it, though, could be to replace 1s2 with a helium, and then with helium's electron configuration, and then just add the next necessary electrons. The idea being we got to here and filled the 1s shell, and we filled the entire row 1. And then we'll just add the additional electrons needed to make a neutral carbon's electron configuration. When we go to nitrogen, we'll have this. The electrons will spread out, and we'll have 1s2, 2s2, 2p3 for nitrogen. For oxygen, we're going to see that electrons are going to be forced to be paired in a 2p orbital because we now need to put 4 electrons in here. Each orbital can only hold 2. So the idea is that we've got 1 electron in the px orbital, 1 electron in the py orbital, and 1 electron in the pz orbital. But they can all hold 2. So we're going to have to be forced to have a pair. So we could have 2 electrons in the px orbital, 1 in the py, and 1 in the pz. Electrons are repelled by each other. So for oxygen, we can just do this. This will be 1s2, 2s2, 2p4. For fluorine, we'll see that the 2p orbital is almost fully complete. We're going to have this, and that'll be 1s2, 2s2, 2p5. If we have 6 in the p shell, then that's going to complete the p shell. And that's what will happen here with neon. Neon will have 10 total electrons, and energy level 1 and 2 are complete. This is 1s2, 2s2, 2p6, which is the same as putting neon with brackets around it. So now we'd like to go on to a much larger atom, potassium. Let's see where it's found on the periodic table. Potassium is here in row 4. So let's see what it takes to make a potassium atom. We're going to fill the 1s subshell, the 2s subshell, we'll fill the 2p subshell, we'll fill 3s, and then 3p. Next, we're going to go on to 4s and just put 1 electron in it, and that'll represent potassium. Alright, so let's fill this, and energy level 2 as well. We're going to fill 3s and even 3p. Notice that 3p does get filled first before 3d. And then the funny thing is, according to this chart right here, after 3p does not come 3d. After 3p, we're going to go to 4s. And that's where our final electron is going to go for potassium. So let's put 1 electron here. That's the energy level diagram for a neutral potassium atom. It can be written as 1s2, 2s2, 2p6. Then we'll go to 3s. We'll fill that with 2 electrons. We'll go to 3p and fill that with 6 electrons. And finally, we'll put 4s1. This could be written as have an argon electron configuration plus 1 more electron. we can see that argon was the final element in the 3p shell. So if we just write that with brackets around it, it tells us that a neutral potassium has everything that argon has and just one more electron in the 4s shell. To complete the diagram for calcium, it's going to be very similar to potassium. We'll fill all the lower level shells. And then we're just going to do 2 electrons in the 4s. Calcium's electron configuration then will be 1s2, 2s2, 2p6. We'll have 3s2, 3p6, and 4s2. Or in other words, argon with 4s2. Okay, when we go on to scandium, we'll see that it's in an unusual position in the periodic table. Scandium is found here at the start of the 3D subshell. So a neutral scandium will have everything that a neutral calcium has, but with one extra electron in the 3D subshell. So let's draw the diagram for calcium first, and we'll see if we can just add one more electron. That's the diagram for calcium. We need to add just one more electron in the 3D subshell. We can see in the orbital filling diagram that after 4s, we will go to 3D. And that's what happens with scandium. Scandium will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we'll actually have to write 3d1. For titanium, we're gonna follow a similar approach as for scandium. Titanium is the second element here in the 3D section. So we'll want everything that scandium has, but we'll put one more electron. That was the diagram for scandium. For titanium, we're going to need one more, and we won't put it in the same orbital that first electron was in. We want to use Hund's rule and spread them out until it's necessary for them to be paired. So now we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and we'll go to 3d2. Here we have iron, and according to the periodic table, iron is the 6th element in the 3D section. Since iron is the 6th element in the 3D section, and there are 5 different orbitals in the 3D, what we'll do is we'll put an electron in each of those 5 different orbitals. But iron actually has 6 electrons in the 3D. So what we'll do is create a pair in one of the orbitals, and the others can have their own electron. This can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, as we can see, S types of shells can only hold 2 electrons max. P shells can hold 6 electrons max. D subshells can hold 10 electrons max. And F types can even hold up to 14. So 2 electrons max in each of these. We can have 6 electrons max. Here we can have 10 electrons max, and here we can even have 14. Okay, notice that there is just one orbital in the S type. There are 3 orbitals in the P type of subshell, 5 orbitals in the D type, and 7 orbitals in what's called the F type of subshell. The D subshells are going to all be here in the middle. This is going to be 4D here. For my last example, we'll do a diagram for rubidium and write its electron configuration. So rubidium is found here in what would be called the 5s subshell. So we're going to fill everything up through krypton and then just put one more electron. Okay. After 4s, we want to completely fill 3d, and after 3d, we'll fill 4p. So let's fill 3d here. Next, we'll fill 4p. And this is going to be everything that krypton has. It is 1s2, 2s2, 2p6, 3s2, 3p6. Then we see that the 4s shell is full. We filled 3d, which holds 10 electrons, so that's going to be 3d10. We also filled 4p, and that can hold 6 electrons. This is krypton. But we're going to go one step farther to make rubidium. We'll put 1 electron in the 5s shell. So we'll have 5s1, and then the electron configuration is complete.